me, I'd like to welcome everybody here this afternoon to a special talk where we're delighted this afternoon to have Dr. Stephen Wolfram giving this presidential colloquium this afternoon. In the way of introduction, Dr. Wolfram received his PhD in physics from the California Institute of Technology. He was advised in that by Richard Feynman and Murray Gell-Mann, Nobel laureate physicists from Caltech. After his PhD, he stayed at Caltech in a faculty position. And in fact, while he was at Caltech, I think his interest in mathematical computation, scientific computation began. There was a mathematical symbolic language called SMP that he worked on at that time. From Caltech, he moved to the Institute for Advanced Study at Princeton University. While at the Institute for Advanced Study, he worked on a number of fundamental ideas in having to do with the theory of cellular automata. In particular, he was one of the first people to unleash the power of computers on one-dimensional cellular automata with nearest neighbor rules. He was able to study those, to classify them in ways that had never been done before. From there, he moved, by the way, at the Institute for Advanced Study in Princeton is where I first met you. I should say Stephen interviewed me for my first job out of university. I went from university to a company in Cambridge, Massachusetts called Thinking Machines Corporation. I think you were consulting for them at the time. And they told me to go to the Institute for Advanced Study and meet you in the lobby there, and I did that. And you were my first interviewee for a job, or interviewer for a job. So from there, he went to Thinking Machines Corporation for some number of months, and that's where I overlapped with him and got to know him better. During that time, he was doing some fascinating work on cellular automata models of fluid dynamics, discrete models of particles moving about on a lattice that could simulate the flow of a fluid. And he wrote some of the first seminal papers on that subject. We're talking now mid-1980s, 1986 perhaps. From there, he moved to the University of Illinois at Urbana-Champaign, where he became the director of their Center for Complex Systems. And at this point, he was really thinking about Mathematica and the Mathematica software project. In fact, even while he was at Thinking Machines, I remember one day you put a floppy disk on my desk and told me to try out this new symbolic mathematics software, and it turned out that was a beta pre-release version of Mathematica. I have used Mathematica for my work ever since then, continuously, until now. In addition to Mathematica software, Wolfram Research also has, there's many number of innovations that have come from there, but some of the ones you may be familiar with are the Wolfram Alpha search engine, and which underlies Siri on the iPhone and a number of other products as well. More recently, the Wolfram language, programming language, which is now bundled with Raspberry Pi hardware, and is thought to be an innovative new language that will be relevant to the Internet of Things, as they call it, which is one of the things that IT professionals look at in the future. As I said, we are really delighted to have him here today, and without further ado, I'd like to welcome him. Please join me in welcoming Dr. Stephen Wolfram.
Thank you very much. Yes, it's. I've known Bruce for 30 years now, and when Bruce told me he was running this university here. He said, you should come and visit Armenia sometime. So I'm here now. I'm very happy to be able to visit at this time. So I wanted to try and tell you a little bit about some of what I've been doing in computation and some of what I think it means for the future of science and technology. Basically, as Bruce sort of indicated, I've pretty much done 3 or 4 big projects in my life. Mathematica, a new kind of science, which I'll talk about, Wolfram Alpha, and now the Wolfram language. And in terms of the sort of flow of what I've done, it's sort of been an alternation between basic science and technology. What's typically happened is I've done some basic science, that's let me figure out how to invent some technology. I built some technology, that's allowed me to go further with basic science, which then feeds back into producing technology and so on. And I've gone through in my life so far, I don't know, half a dozen or so cycles of that process. I think, let me start off perhaps by showing you a few of I'll just show you, for example, Wolfram Alpha. So the idea of Wolfram Alpha, many of you, actually I'm curious, how many of you have used Wolfram Alpha? Okay, that's good. So, so kind of the concept of Wolfram Alpha is take the knowledge that exists in the world and try and make it computable. In the sense that if there's a question that can in principle be answered on the basis of knowledge that exists, make it automatic to get that question answered. And that's a hard problem. It has many different parts. First of all, you have to encode that underlying knowledge. You have to be able to get all these different sources of data for different kinds of things. You have to be able to organize them, make them computable. Then usually when somebody wants to know something, they don't just want to get an individual piece of data. They want to compute something on the basis of that data. So you have to encode all the kind of methods and models and algorithms and so on that have been developed in science and engineering and finance and other places and put those into the system. And the next problem is, okay, you can compute all this stuff inside, but people have to tell you what to compute. And so then you have to be able to figure out how to take the language that people use to describe computations and understand that. You have to be able to understand natural language. So if we ask Wolfram Alpha, we can say things like, what is the integral of, x squared cosine cubed x or something, and it'll go off hopefully and figure out there's the answer, and then it'll give us kind of a report about the answer. So it'll say, here are some plots you might want to see, here are some alternative forms of the integral, etc., etc., etc. And if you have the pro version, it will also show you, for example, a step-by-step solution for the integral. Actually, I should say that this step-by-step solution is really kind of a fake, because this step-by-step solution is built for humans. It's not the way that the underlying system computes the integral. The underlying system has some powerful algorithms for computing integrals that would not really be easy for humans to understand. But when you ask it to show you steps, it will show you the steps that a human would have to go through to do the same thing. So Wolfram Alpha knows about kind of how to compute mathematical kinds of things. It also knows things like things about the world. So if I say, what is the population of Armenia, for example, it should be able to give me an answer to that, and it should show me a historical plot and so on. If I say, what's the population of Armenia divided by, Chile or something, it can understand that question and will then try and give us an answer and show us plots and so on. So, and the kind of the idea in all cases is there's all this data that's coming into Wolfram Alpha, And when you ask it about something, it will try and give you a sort of report about the most relevant things. So here I asked it about the International Space Station, and it will show me where the International Space Station is right now. It'll show me things about when the International Space Station will be visible here, and so on. So kind of the idea is just be able to know about, let's ask it about the weather. It knows we're in Yerevan, so it's going to tell us what the weather is here now, and it should be able to give us some information here. Let's see. Okay. It's might be able to give us some information about forecasts and so on. I'm surprised it isn't actually showing us a plot of temperature as a function of time. In most places it would do that. Let's try one more time. Sometimes it, but in any case, we're able to. We have all this data about. Also, there we go. There's a nice plot. So that's the temperature as a function of time for the past few days in Yerevan. We could say, show us that plot for the past 10 years, and we'll discover that, wow, it gets fairly cold here in the winter. So in any case, the kind of the objective in Wolfram Alpha is to know about all sorts of domains of knowledge and to be able to automatically compute answers to questions. So it's a big project, and it's kind of been building on many years of work that I've done. Maybe I should start off and sort of tell you, and this is also, Wolfram Alpha is also what is now making possible this thing we call the Wolfram language, which is kind of our new big thing that is just about to be unleashed on the world. But maybe I should, before I get to that, maybe I should talk a little bit about the trajectory that kind of led me here. Actually, no, you know what? I'm going to talk about the language first, and then I'll tell you how I ended up building all of this stuff. So let me start up the Wolfram language. So again, we can start by doing very simple kinds of things like this. We can now. So the idea of the Wolfram language is to have a language where as much as possible is automated. So most computer languages are basically ways to tell the computer precisely, step by step, what it should do. And then maybe the language provides what you need in order to build up a big program out of those very small steps. The idea in the Wolfram language is to do something different. It's to build into the language as much knowledge as possible about things. So, for instance, we can go and we can just compute stuff in the language. I don't know, there's 1,000 factorial or something. It's nice and fast to compute. We could, say something like, factor some polynomial, something like that. We can do all kinds of algorithmic things. Like let's pick up an image here. Hopefully this will work. Let's see. Okay, there we go. There's a camera. Okay, let's pick up another image of you guys. Okay, there we go. So now we've got this image, and we can start doing computations on this image. So, for example, we could say, let's say, for example, we want to do edge detection on that image. We can just, in the language, we can just go ahead and say edge detect that image, and we get an answer like that. Or we could say something like, we could say something like, go ahead down here and say dynamically edge detect this current image. And now what will happen is it will just be running all the time, doing edge detection and so on. Yeah, you should be able to. Now we can, we know lots of things about how to manipulate images. We could, for example, pull in a Facebook friend graph. And actually my Facebook friend graph is pretty boring, and it's also always a nuisance to set up pulling it in. So let me make a fake Facebook friend graph. Let's say I have 200 friends, and I have altogether 500 connections between those friends. So there I got a kind of a random graph with those characteristics. And now we can take that random graph and we can go and do all kinds of computations on that graph. So, like, for example, I tell it, make a plot that shows the communities of people within that graph, those kinds of things. So the idea of the language is to have all of this knowledge about how to deal with images, or, for example, let's say we do something like we make a 3D graphic. Let's say something like this. Now we can go ahead and manipulate that 3D graphic, but we can also do things like we could say something like what's the area of a sphere, and this that's the unit sphere, so it tells us the area of the surface is 4 pi. We could go on and do all kinds of other things involving geometry, let's say. So let's say that the notion in this language is build in as much knowledge as possible. We could also ask it things about sort of the real world, and here, for example, I'm saying when is the sun going to set today? And let's say we ask it. Let's say we say sunset tomorrow. Let's try to see what happens here versus sunset today. And so now what it should do. Okay, so it's telling us the days are getting slightly longer. The time between sunset tomorrow and sunset today is just a little bit more than 1 day. So we can go ahead and do some of the kinds of things that we have from Wolfram Alpha, where we know things like where we can actually compute with entities like countries. So here, Armenia is an entity, and we can say, well, let's do this. We can say the entity value for Armenia of flag. And so here now we will get a picture of the Armenian flag, and we could now say, let's say, what are the dominant colors in that flag? There we get those colors, and we can go and do all kinds of computations from this. Or, for example, let's say let's say we do this. Let's say countries in Europe, and then let's actually. I have a good question. Okay, now let's say let's try and find the flags for all countries in Europe. This might take a little while. There we go. Okay, so now we've got all these flags, and we could, for example, we could say for all these flags, we could do something like say, what are the dominant colors in those flags, and we get a whole list here of dominant colors in those flags. Or, for example, we could take those flags and say, I'm just telling it the result on line 22. Okay, so there we made a collage of all those flags. Or we could go ahead and say, and we can always do all these other kinds of things that I showed you. I mean, we could say something like, edge detect that collage there, and so now I've got that kind of thing there. And I could say, for example, I don't know, I could take this and let's see what I do. Maybe I could take this and I could say, partition that image into little pieces of, let's say, 10 by 10 blocks, let's say. And now we should get a huge number of those. There we go. There are lots of little 10 by 10 blocks that we just got. And for example, one thing we might do, just for fun, is let's take all those blocks and let's see how many of them. Let's make a count of how many identical blocks there are at that size. Okay, so that's kind of interesting. So there's lots of black ones. There's 8 that have that particular pattern of pixels, and so on. We can do all kinds of computations from this. Actually, here's one that it's kind of fun to try. Let's try taking the set of flags that we got, flags of Europe, and let's ask the question. Let's do something that's kind of related to machine learning. Let's say we want to define a function which takes all the flags and finds out which of those flags is nearest to which of those. If we take the Armenian flag, which of the European flags is the Armenian flag nearest to? So let's go back here. Where do we have the Armenian flag? There we have it. Let's go down here, and let's say, for example, the nearest, and then the Armenian flag. And let's actually say the 5 nearest flags. Okay, so it's funky. I don't know why I can see why it would pick the first one. I'm not quite sure why it picks the second one. But maybe it just decided there was a lot of red on that one or something. But this is the type of thing that we can do. And so the idea in this language is just build in as much as possible right into the language and try and sort of automate as many things as possible. So for instance, another thing we could do is, let me actually show you. Okay, so another thing we can do is we can say manipulate things. So let's say we plot a graph, a graph of sine x from 0 to 10. Okay, now let's say, manipulate the graph of sine ax with a going from, let's say, 1 to 10. Okay, so now we get this kind of control here where we can say, we can adjust that parameter and move it around like this. Or we could, for example, we can manipulate anything. So for instance, we could say, we could be factoring a polynomial, for example, and we could say, manipulate factor x to the n minus 1, and now we'll get sort of this algebra being manipulated in real time like this. So this manipulate function lets you do any of those kinds of operations. Or for example, we could take, let's do this. Let's get this current image again, and let's go ahead and take that image, and let's say manipulate that image. Let's manipulate. What's a good example? Let's manipulate binarizing that image with a different threshold, and then let's say threshold goes from 0 to 1. And so now what we'll get is something where, okay, at threshold 0 you can't see very much. As we increase the threshold, we'll gradually be able to see more and more of the scene, and eventually it'll go black. So this is how we can, again, apply these kinds of operations into the system. So, as I say, the goal is to build as much knowledge as possible into this language. This is sort of the world's first kind of knowledge-based language, where the goal of the computer language is to automate as much as one can in the system. And it has knowledge about, let me show you another kind of knowledge that it has that's quite interesting. So if I say something like geographics, let's say I say a disk around here with radius, let's say 4 kilometers. 4 kilometers. So this is saying make a geographic graphics with a disk of 4 kilometers centered around. Oh, great. Okay, that's not going to work. Okay, this is the problem with showing you things that are still under development. I think this may not work. Let's try it one more time. I think it may not work right now. Oh no, it did work. Okay, that's cool. So, there we have street maps of the Earth, and this is now a plot of showing center there and so on. And we could go and zoom in. We could probably make this. I don't know. Let's make that instead of 4 kilometers. Let's make that 4,000 kilometers. Okay. Let's see what that does. Okay. There we go. So now we have to, as you can see, it's doing some fancy map projection and so on to get to this point. Actually, probably what we could do if we say geo-range arrow world, it'll show the thing for, it'll show that. This is okay. For some reason, this is there's some piece of piping in the complicated world of the web that is slightly broken right now. But in any case, we saw it do something pretty good before. We could, for example, say something like, what's the distance between, let's say, Boston, where I live, and here, and that should then, oh great, I think it's now being jinxed. It's now horribly broken. Okay, this would normally work beautifully. So in any case, the question. So one question is, how does this whole system work? How does a language like this, how is it put together? So one very important attribute of this language is that it's symbolic. So normally in a computer language, if you just have a variable x, and you just type in x, it will say, oops, I can't tell you about what's going on here because x is undefined. In the Wolfram language, it's a symbolic language, so x can just stand for itself. And we can do computations involving just the symbolic variable x, and we'll get results. And that's important because when we're making something like I don't know, let's say we make a 3D graphic of a tetrahedron or something, that again is just another symbolic expression. We can see what the expression is. We can say what's the explicit symbolic expression. It just looks like this. It's another symbolic thing, just kind of like